Hello, everyone, and welcome to Physics Lab. So this lab is on Newton's second law. And this lab is one of those labs that's very similar to all of my lab sections. So this video lecture will be applicable to Physics 212, Physics 207, and 206. Okay, so this particular lab is very similar. So what is Newton's second law? Well, let me jump over to the iPad to describe this. Okay, so let's say I have some object, right? And let's assume that there's some forces acting on the object. I'll draw, say, force 1, say in this direction. This is F1. And let's say I have force 2 in that direction. This is force 2. So first of all, I could find the net force, right, acting on this object. The net force basically means the sum of the forces. I need to add all the forces together. So if we just do this graphically, right, I can move the tail of F2 to the tip of F1. So it's sort of like this. And if I draw a vector from the tail of F1 to the tip of F2, that's going to be my net force, right? That's the sum of all the forces acting on the object. Now, what Newton's second law says, so now this is Newton's second law. It says that the net force, which is really the sum of all the forces, so I just added up all the forces vectorially, that's equal to the mass times the acceleration of the object. So mass times acceleration. So this object has some like mass m here. Now, what this tells us, remember, the net force is a vector, right? The acceleration is a vector. Vectors have both magnitude and direction. The mass here is just a scalar. It only has magnitude. So this tells us that the direction of the acceleration of this object is same as the direction of the net force. So in this case, this object is going to accelerate in this direction, same as the net force. That would be the acceleration. Another thing that's interesting is since this is a vector equation, it's kind of an efficient way of writing 3 equations in one, right? So really you could split this up into its components, and it's true that Newton's second law applies for each component. So I could write this as the sum of the forces in the x direction equals m times acceleration just in the x direction. Then sum of the forces in the y direction equals m times ay. And then sum of the forces in the z direction, if you have 3 dimensions, is m az. So this set of 3 equations here is equivalent to this one vector equation. So the one vector equation is just a very efficient way of writing those 3 equations, okay? And this is if we have 3 dimensions. In lab, we're going to focus on 2-dimensional problems. So really, we're just going to use these first 2 equations. We won't talk about z, right? We won't talk about the 3rd dimension, just x and y. Okay, so that's Newton's second law. Okay, so basically the purpose of this lab is to verify Newton's second law. So we have this situation, and again, you want to watch my video where I actually show you the equipment and like how I collected the data using a smart timer. I have a cart on an air track. Remember, the purpose of an air track is to reduce friction, right? So friction is negligible. We can just ignore friction. And connected to the cart is a string. It goes over a pulley, and then we have a hanger here. So think of it as a suspended mass. And what we're doing is we're starting this system at rest, releasing it. The cart's going to accelerate to the right, so with some acceleration A, and the suspended mass will accelerate downward, right, with the same acceleration because they're connected by the string here. So we can measure, and you'll see this if you watch that video on me collecting the data, we can measure the acceleration experimentally using something called a smart timer, right? And we do that for different conditions. Basically, in the first part of the experiment, we're going to vary the mass of the cart, but leave the suspended mass the same. In the second part of the experiment, we're going to leave the mass of the cart the same and vary the suspended mass. So under different conditions, we're measuring the acceleration, the experimental acceleration of that system. And then what we want to do, and I'll do this now on the iPad in a minute or two, is we want to also compute theoretically, using Newton's second law, theoretically what the acceleration of that cart should be, of that system, the cart and the suspended mass. And then ultimately, we're going to compare what we got theoretically to what we get experimentally, right? Remember, experiment is measured using the smart timer, using the equipment. Theoretically, we're going to derive mathematically using Newton's second law. So actually, let me do that now. Let's derive what the acceleration of the system should be. Okay, so I'm going to go back to the iPad. Okay, so here's the situation, right? Here's, let's say, the air track. Here's the cart, right? There's a pulley here. There's a string, connects the cart, goes over the pulley, and then you have the suspended mass. I'm going to call this, I'll call the cart M1, mass 1, and the suspended mass M2. And we know that when we release this from rest, this whole thing is going to accelerate to the right. The cart will accelerate to the right, and the suspended mass will accelerate the same acceleration downward. So the whole idea here is to compute A, to find that acceleration A. Okay, so to do this, what we need to do is we need to apply Newton's second law to each object that's in the system. So I'm going to first start with the cart. And I'm going to draw what's called a free body diagram. So I'm going to draw the cart. I'll just draw it as a small little square there. And I want to figure out what forces are acting on that cart. What are the forces acting on that cart? So if you think about it, well, we have several forces, right? We have the weight of the cart, right? That's like the gravitational force that's acting down. And we know how to compute that, right? So I'll call it weight 1, it's really a vector. It's equal to M1G. Then the air track itself is exerting a force up on the cart, right? It's like a contact force. It's a force that the surface exerts on the cart perpendicular to the surface. That's a normal force. So we have a force upward, a normal force that looks like this. We're ignoring friction, right? Normally we'd have a force that points to the left, but we're ignoring friction, so we don't need that. But there's one other force. The string is also connected to the cart, right? So the string must be exerting a force on the cart. So we call that a tension, right? Tension in the string. So that's to the right. That's T. Okay. Now that we have all the forces drawn, we have to create what's called a reference frame, right? Some reference frame, like an XY coordinate system that we can use as a reference frame. And it doesn't matter how we orient the reference frame, but in this case, it probably makes sense since we know the cart is accelerating to the right. I'm just going to use the standard frame where I have X going to the right, like this, and then Y vertically. So Y is positive going up. This is Y. Okay, now that I have that, let's use Newton's second law in both the X and Y direction. So we're going to apply Newton's second law to the Y direction and to the X direction. I'll do the Y first. So I have sum of the forces in the Y equals the mass of the car M1 times AY. So when you're first learning this, it's probably a good idea to write out all of the components. So I have 3 forces, right? So I want all the Y components of those 3 forces. So I can write this out. I want the Y component of N plus the Y component of T plus the Y component of the weight. That's got to equal M1 AY. Okay, so what is the y component of n? What is the y component t? What is the y component of each of those forces? Generally, this is the trickier question, right? You have to do a little more work because generally, let me just do a little bit on the side here. Generally, you're going to have a vector like this. Right, let's say that's our vector. And to find the y component, I'd have to project onto the y-axis. To find the x component, I project onto the x-axis. So this would be like vx. This is vy. I'd have to know the angle. And I could do that, right? If I know the magnitude of v, I can use v times cosine of theta to get vx and v times sine theta to get vy. So normally we have to use a little trigonometry to get the components. But in this case that we have here, these vectors are lying right along the axes. So it's much easier. So if we want the y component of n, how much of that, just ask yourself, how much of that vector n, the normal force vector, is acting in the y direction? Well, all of it is, right? There's nothing, none of it is in the x. There's no projection of it, no component in the x direction. It's all in the y. In fact, it's all in the positive y direction. So this, the ny, is really just n. What about the tension? How much of the tension is acting in the y direction? Well, it's right along the x. There's nothing in the y direction, right? So 0 of it is in the y direction. And then the weight, how much of it is in the y direction? All of it, but in the negative y direction. So this is going to be, I'll write it as negative m1g. And in this, this object, this cart, is not moving in the y direction at all, right? It's not leaving the air track. So the acceleration in the y direction is going to be 0, right? So if this is 0, that means this whole term is 0. So then if we solve for normal force here, we're going to find normal force is equal to, bring the m1g to the other side, I'm going to get positive m1g. So that's correct, right? In this case, the normal force is just equal to the weight of that cart. And this would be very useful if we had friction, because friction depends on a normal force. But since we don't have friction, this is not so useful in today's example, right? But I'll leave it there. It's a correct equation. Normal force is equal to the weight of the cart. All right, now I go to the x direction. So I have sum of the forces in the x direction equals m1ax. So I'll do the same thing. I want the x component of n plus the x component of t plus the x component of the weight. That's going to equal m1ax. But what is the x component of the normal force? Well, the entire normal force vector is in the y, right? There's no component in the x. So this is going to be 0. What's the x component of the tension? Well, all of the tension is in the x. In fact, it's positive. So I'm just going to call this t, right? It's the magnitude of the tension. And then what is the x component of the weight? Well, none of that weight vector is in the x direction. So this is 0. And that's going to equal m1. And then what is the acceleration in the x direction? That's what we called a, right? If you look back here, remember we're calling this a. So I'm just going to call that a here. So this is ax is just a. So this equation says that t equals m1 times a. So that's an important equation, right? I'll box that. Okay, so we applied Newton's second law to the cart. Now we're going to do the same thing to the suspended mass. Remember, the suspended mass is the one that's going to accelerate downward, right? The hanger. So let me do that over here somewhere. Let's say this is the suspended mass. Now, what are the forces acting on the suspended mass? Well, it has a weight, right? So that acts down. It's a gravitational force that the Earth exerts on the suspended mass. And we know that, I'll call it weight 2, it's equal to m2g. And then the only other force acting on the suspended mass is the string, right? The string is connected to it. So there's a tension in the string pulling up. So I'm going to call that T. So tension in the string. Now, just like before, we need to create a reference frame, right? We need a coordinate system to use as a reference frame. We could use the standard XY, but that gets a little confusing because then it's accelerating in a negative direction. So because we know it actually is going to be accelerating downward, right? Remember, this thing is going to accelerate downward with acceleration A. I'm going to just call the downward direction X, which I'm free to do, right? So I'm going to make this my X, positive X, and then perpendicular to it would be my Y. I kind of like rotate my coordinate system, right? And you'll see why that's useful later. And you're free to do that. You're free to put the inertial coordinate reference frame, the coordinate system, however you want, orient it however you want. So now let's apply Newton's second law. So let me do the Y direction first. So I have the sum of the forces in the Y equals M2 now, right? AY. So I want the Y component of the tension plus the Y component of the weight. That equals M2 AY. Okay, now you got to be careful. Remember, I defined Y to be in this direction, right? X is in this direction. So how much of the tension and how much of the weight are in the Y direction? None, right? Those vectors are in the X direction, what I'm calling the X, either positive or negative X direction. None of it is in the Y direction. So this is basically 0. The Y component of the weight is 0. And we know it's not moving in the Y direction, so it can't be accelerating in the Y direction. So this is 0. So this equation just says 0 equals 0, which is true, but it's not really helpful, okay? So now I'm going to go to the X direction. I'll do that right here. So sum of the forces in the X equals M2 AX. So again, I want the X component of the tension plus the X component of the weight. That's equal to M2 AX. Well, how much of that tension is in the X direction? All of it. And is it positive or negative? Based on my definition, it's negative, right? Because remember, downward, I'm calling positive. So this is just going to be negative all of T, right? Negative all of tension. And then what about the weight? How much of the weight is in the X direction? All of it, and it's positive, right? Because it's acting downward. So this is just M2G. And that's got to equal M2AX. But what is AX? AX is the same A as before, right? It's the same acceleration that the cart had. So this is going to be A. And again, very important equation. I'll box this. This is like the second important equation. Okay, now remember, our whole goal is to compute A, right? The acceleration of this system. We're going to know, so if I look at my two equations now, we're going to know M1 and M2. This is the mass of the cart. This is the suspended mass, right? We can mass these things. We can weigh them on a scale, right? So we know those are given values. We know that. We know G. If we're talking about CGS units, right, centimeters per second, centimeters per second squared, G is going to be 980, so that's known. But we don't know tension, we don't know acceleration, don't know T, don't know A. But I have two equations, they're two linear equations in terms of two unknowns, T and A. How do I solve two linear equations by two unknowns? You guys may have learned different techniques like substitution or elimination, or maybe even matrices, using matrices. So I'm just going to use substitution, where I have a T in this right-hand equation. So where I have a T here, I'm going to substitute in this T, which is M1A. Okay, so I'm going to just plug this in for T here. So I have minus M1A plus M2G is equal to M2A. Let me bring the A's together, because remember, my whole goal is to solve for A. So I'm going to add M1A to both sides. So I get M2G is equal to M1A plus M2A. Now, let me factor out that A. So it's common to both terms, the right-hand side, so I can pull out, and I'm left with M1 plus M2. Then I'm just, to make it clear, I'm going to write this on the left-hand side. And then finally, to get A by itself, since it's being multiplied by M1 plus M2, I'm going to divide by M1 plus M2. These cancel, and that's my final answer, right? So I'm going to get A, the acceleration of the system, is M2G divided by M1 plus M2. And that is the equation that we wanted to derive. So if I know the mass of the hanger of the suspended mass. So I plug that in there and there. If I know the mass of the cart and I know G is 980, I can plug that all in, and that must give me the acceleration of the system. So this is like our predicted theoretical acceleration today. So it's predicted. Predicted acceleration. That's what you want to use. When it says theoretical or predicted acceleration, just use that formula. Okay, so now we're sort of like verifying Newton's second law, right? Because we're going to compare the values that we got from here, like predicted, to what we got experimentally by measuring it directly with a smart timer. So let me go back to the handout. Okay, so again, we now have our predicted acceleration, right? It's m2 times g divided by m1 plus m2. Okay, so for the first part of the experiment, let me just bring up the table here. First of all, there's going to be two conditions for the first part of the experiment. Again, we're going to vary the mass of the cart. So in the first condition, it's just the mass of the cart alone. And the second part is the mass of the cart. We're going to make it a little heavier by adding these like two cylindrical weights, these two additional weights. Okay, again, this will make more sense if you actually watch the video on how I collected the data using the equipment. If you're watching this video because you missed lecture, make sure you get these values from your lab partner. Okay, and again, if you can't for some reason, just give me an email, send me an email, and I can give you some values for this. So this is going to be some mass in grams. This will be some heavier mass in grams. The hanger, though, is going to stay the same. It's a hanger with a small metal weight. That's going to be the same for both conditions. Okay, so we're just varying the mass of the cart, not the mass of the hanger for this first part of the lab. Now, what these values are here is basically I collected, or your lab partners collected, the acceleration using the smart timer for 10 trials for the first condition, and then 10 trials for the second condition. So question one, what you need to do is you need to just average these acceleration values. So that's the average right here. Should be, I believe it's to 1 decimal place. You want to round to 1 decimal place. And then you're also asked to compute the percent experimental accuracy. Okay, we've done that a bunch of times. So go back to that original handout in like lab 1 if you need to. But remember, you have to find all the absolute deviations, how far each value is away from the mean, average these absolute deviations, round to the resolution of the instrument, which is 1 decimal place again. And then it's always going to be the average absolute deviation divided by your average acceleration times 100, right? And then make sure you show me those calculations. Okay, question 2 is to compute, so using that equation that we just derived up here, right? A equals m2g over m1 plus m2. Compute the predicted accelerations. So for the first condition, compute that and show me that calculation. And then for the second condition, where you have the heavier cart, compute the acceleration and show me the calculation. These experimental accelerations, these are just your averages here. So you can copy these down. So average acceleration for the first condition, average acceleration for the second condition. It's going to go right in here. Question 3 is now we're going to compare them, right? So compare what you predicted to what you measured using the smart timer, or what you calculate as your average here from the smart timer. How do you compare things? You're going to compute a percent experimental error. So you basically subtract these, make it positive, and then divide by the predicted. The predicted accepted is one you always divide by, right? And then times 100. And then make sure you show me these calculations. Okay, question 4. This is from the lab manual. It says, so it says, based upon the results that you obtained in this experiment, how does the acceleration of the cart vary with its mass, given that the suspended mass is maintained? And my hint is, well, first of all, you could answer the question by looking at your data, But my hint is it might be easier just to use this equation, the theoretical equation that we derived. So if the suspended mass, M2, stays the same, right? So same value, that's not changing for those two conditions. And G obviously is the same, it's 980. If we increase the mass of the cart, so if M1 becomes larger, what happens to A? What's going to happen to the acceleration, right? So that should help you answer that question. And then the next question, question 5, says, based upon the results that you have obtained in this experiment, how does the force on the cart need to change with the mass of the cart in order to impart the same acceleration? Again, you might be able to intuitively answer that from your data, or another way is to look at the first equation that we derived, which is this right here. So T, remember, on the cart, we found that the tension on the cart, this is like the net force, which is the tension on the cart, is equal to the mass of the cart times acceleration. So it's saying if we increase the mass of the cart, but we want to maintain the same acceleration, we want the same acceleration, what has to happen to the tension value? That's basically what it's asking. Okay, and I'll let you think about that. Okay, then we get into the next part of the experiment. And in this part, it's kind of the opposite. Now we have 4 conditions, but instead of varying the mass of the cart, we're keeping the mass of the cart the same. It's going to be the mass of the cart with the 2 weights. That is going to stay the same for all 4 conditions. The 4 conditions are, we're going to vary the mass of the hanger. So the first condition is the hanger plus small metal mass, right? So it's light. Second condition is hanger plus small metal plus large plastic, so a little bit heavier, a little bit more massive. Then hanger plus large metal and large plastic, so a little bit heavier still. And then hanger plus small metal, large metal, and large plastic, so a little bit heavier. So we're just increasing the mass of the hanger, right? So actually, if you look in the table here, this, I don't know why this is run. This would really be conditions, right? These are your 4 conditions. So this is the hanger plus a small metal weight. Second condition is hanger plus small metal plus large plastic. So it's a little bit heavier, right? So you're going to have all these values. Again, if you don't have them, get them from your lab partners or contact me if you need them. These are going to be like in grams and they're going to be increasing. And then all we did here is we collected the acceleration of the system for 5 trials. Okay, so we have the same, just like we did before, we collected acceleration for 5 trials. Now, what you're asked to do in question 6 is, first of all, find the average acceleration for each of these conditions. And then the last column here is compute the tension in the string. And we're going to do that using this equation. This is basically the second equation that we derived when we came up with the equation for the acceleration. So to calculate tension, you're going to plug in M2, right, which is your mass here. So it's going to vary, right? Depends on your condition here. Times G is 980, right? That's a constant. And the A here is your average acceleration. Now, you're going to find that you're going to get very large numbers, which might be confusing at first. You might say, oh, I think I did something wrong. You didn't. Like if you get like 6,000 something here as a result, that's correct. It's just because in CGS units, which we're using today, centimeters, grams, seconds, forces are in what's called units of dynes. And they just happen to be much larger than the units of newtons, right? It's like they're off by like 10 to the 5th, like 100,000 times as large. So you're going to get values of like 6,000, then they're going to increase. I think the last one is like 17,000. So don't worry if you get that. That's correct, okay, that you get those values. Okay, so fill in that table, calculate the average acceleration, calculate the tension in the string. Now what you're going to do is you're going to plot tension versus acceleration. So tension is on the y-axis, acceleration is on the x. All right, let me outline this on the iPad. Okay, so we're plotting tension on the y-axis. This is in dynes versus acceleration in the x-axis, which is in centimeters per second squared. You want to make sure you include 0, 0 as one of your points. And we know, so we know the equation, right? Remember on the cart, we have the equation T equals M1A. So this kind of has the form like of a line, right? This is like Y equals MX plus B, where B is 0 in this case. So if you look at your data, hopefully it looks pretty linear. So you want to do a linear fit. And then the slope is going to be really important, right? Because what does the slope represent? Well, if we compare over here, right, the Y variable is our tension, the X variable is acceleration. So the slope must be the mass of the cart, right? The slope must be M1. And remember, in this part of the experiment, we left those two cylindrical weights on. So really the M here is the mass of the cart with the two cylindrical weights. So I'll say with the two weights. And it'll be in the correct units of grams. Okay, so you're going to do that graph on Pascal capstone, linear fit, right? It'll give you the slope value, and that slope represents the mass of the cart with the two cylindrical weights. Okay, so that value, we're going to call that our predicted mass of the cart with the two weights. So that's going to go right here in this table. So this is the slope from that graph that you just did. The measured mass of the cart with two weights, you already have that. You measured this in the very beginning, right? And again, you got this from your lab partners or you got it from me. So this is the value right here, right? Mass of the cart with the two cylindrical weights. You have that value in grams. So hopefully they're pretty close. You're going to compare these two by computing a percent experimental error. And again, think of the predicted one as like being the accepted one. That's the one you want to divide by. Okay, and hopefully you get a fairly small error here. All right, and then there's one last part of this lab that involves a simulation. So I'll show you guys the simulation in 1 minute. Actually, let me go to that right now. So you're gonna click on this link and go to this PHET simulation, forces in motion. Okay, so here is the PHET simulation. It's called forces in motion basics. And you're going to choose, for this part, we're going to choose acceleration as our option. I'm going to click on that. And we want several pieces of information here. So we want the forces, we want the sum of the forces, values, masses, everything but acceleration. We'll click that later because we want to calculate it first and then compare to what we measured by clicking this later. Now, to make this, so right now the object is this crate, 50 kilogram crate. We're going to make it a little heavier by putting the child on top of the crate, right? So it's like a total of 90 kilograms. And then you're going to set the applied force. So this person or this robot is going to apply a force. We want it to be 300 newtons to the right. By the way, notice here that if I click on this, right? So right now, the person or the robot is applying a 50 Newton force, right? Applied force. But we also have a frictional force that's backwards of 50 newtons, right? It's a static frictional force. Eventually, we're going to overcome that static friction and then the object will start moving. And then we're going to have just an applied force to the right of 300 newtons and then some kinetic frictional force applied to the left. So let's do that. I'm going to bring this up to 300 newtons. Okay. So just based on this information, right, we know 300 newtons to the right, 169 newtons, that's their kinetic frictional force to the left. So if we use Newton's second law in the x direction, we can say sum of the forces in the x has to equal ma. So I want you to calculate the acceleration of the system. And then after he reaches top speed, or the person or the robot reaches top speed, see how it starts slowing down? Because now there's no more applied force. So the only force acting is the frictional force, which is negative. So again, in this situation, I want you to calculate the acceleration. So you can, again, use sum of the forces in the x equals ma. But now the sum of the forces is just negative 169, right? Then you're going to do exactly the same thing again, but now you're going to click on acceleration and actually measure, like get the measured value. So if I go to 300 again, right, as the crate and the child are accelerating, right, they're speeding up, you have this acceleration. So basically it's measured right now as 1.46. And then after the person or the robot lets go, you're going to see a negative acceleration, right? Because it's decelerating, where the only force acting is the friction. So hopefully your value that you compute is close to this. And then when you compute it again, so now you're going to compute it again, hopefully it's close to negative 1.88, right? And you want to show me those calculations. Okay, then you're going to do the same thing again, but now you're going to use just 2 crates as your object. And so here, I'll click on all this information again. First, do it without clicking on acceleration. So apply 300 Newton force. Using sum of the forces in the x equals max, calculate the acceleration of the system. And then if you want, if you can do it quick enough, you can just press this now to measure it, right? And then use the measured value. And then after the system reaches the top speed, right, the robot or person will let go. And then I want you to recalculate the acceleration of the system. So using sum of the forces in the x equals max, recalculate it, and then you can check your measured value by clicking on acceleration and see what you get, okay? So that's all there is to the simulation part. So let me go back again one last time to the lab handout. Okay, so again, you're gonna calculate the acceleration when the person is speeding, when the person pushing the crate is speeding up, right? And this is for the first part, it was a crate and the child on top. And then you're going to record the measured value of the acceleration. You're going to calculate the acceleration when the person no longer is pushing, right? They let go. So calculate the acceleration and then record the measured acceleration. They should be close, right? You don't have to compare these using a percent error or anything, but they should be close. And then you're going to do the same thing again, but instead of the crate and a child, you're going to have just 2 crates as your object. So calculate the acceleration when they're accelerating, speeding up, calculate the acceleration after the person lets go, and then record the measured values. And hopefully you get something very similar. And then show me these calculations. Don't forget to show me the calculations, how you calculated the acceleration. Right? And you should find that they're, if not exactly the same, they're very, very close. Okay, and then that's it for this lab on Newton's second law. Thank you.